Hello students. So now we will be moving on to the second module, and it will be all about earth pressure and retaining walls. So let us see what the syllabus is covering in this module. Here we deal with lateral earth pressure and various types of lateral earth pressures. Then we deal with Rankin's and Coulomb's theory to solve the problems associated with earth pressure, and also we will discuss with earth pressure on retaining walls where there is layered backfill, and finally the numerical problems which were asked for university exams. So what are the situations where there is earth pressure, or we will discuss what is a retaining wall. So you might have seen this retaining wall in many places, and basically we construct a retaining wall either to support a fill, or if we do a deep cutting, we used to construct retaining wall to support that cut, basically to stabilize the slope, that the cut portion, or there may be a chance that the portion which you have cut may fall down, or also when we fill something, definitely it is the same. Again, the purpose is same, that to protect that fill or that cut. So for that we construct retaining walls. So there are different types of retaining walls, and let us discuss about the types of retaining walls. So before that I will just define what are retaining walls. They are structures that support backfill and finally allowing a change of grade, that is a slope change is also possible. Also here in this figure you can see, let us consider this is a hilly area, hilly terrain, and you want to construct a road nearby this, or you are extending you need a plain surface here. So you fill this plain surface with some backfill soil, and now you want this fill, either you can maintain a slope or you can construct this retaining wall. But if you don't have sufficient space to have a reasonably flat slope, then the space is restricted. Then in that case you construct a retaining wall to just to retain that fill. Similarly, whenever you make any cut for any purpose, or you are cutting this soil mass, this huge mass or this huge slope, and you want to have a railway line in between these two slopes, and you can't keep a safe slope because the space is restricted. So in that case you will construct a retaining wall. So this is a natural thing. You have seen, if you are traveling by road or rail, definitely you might have seen a lot of retaining structures, earth retaining structures. So now let us go on to the next section, that is types of retaining walls. So here we can see why the retaining walls are used, and based on the purpose, what are the different types of retaining walls. So here the first one here, this is a embankment. So if you are having an embankment and you can't have a gentle slope or a safe slope on either sides, and the space is restricted, then you go for a retaining wall. So generally this retaining wall is usually used basically whenever there is a restriction for space. If the soil cannot naturally stay on its slope and your area is restricted, then in that case we retain that soil with the construction of retaining walls. And here this figure you can see, here there is a cut and you are having retaining walls on either sides to support that cut. And also whenever a bridge is approaching a road, for that here you have some filling, and there you support that fill, you have a retaining wall here. And here to have water retaining structures, water storage, you construct retaining walls, you construct canals, and on either sides you provide that wall to support that soil, then it is a retaining wall. And then comes the flood walls. To prevent the flood, you construct retaining walls. And also finally sheet piles. Sheet piles are temporary walls which usually if we have to construct something in the soil, we dig out the soil or excavate the soil. And here also, if we need enough space and we don't want to have a slope of the soil inside the excavation to have enough space, For example, if you are constructing a huge pit or you are constructing a group of foundations inside the soil, then you may need more space. Then in that case, what we do is we construct such kinds of sheet piles so that you have enough space inside the soil mass. Okay. And now the various types of retaining walls. You have the gravity retaining walls. That means the retaining wall is stable stable just because of its gravity, just because of its weight. It is stable. That's why you can see here it is moving towards the bottom, and the widening happens. That is, the wall is widening as it moves towards the bottom. And semi-gravity wall may be slightly thinner walls compared to this gravity walls. Then there is a cantilever wall. In cantilever wall, you have a slab and then you have a stem. So this you call as the base slab, and then this is the stem of a cantilever wall, and this will be the backfill portion, and here it is a open space. Then comes the counterfort walls. In counterfort walls, you have counterforts like this. You support this portion, and when you have a huge length of wall, then this is actually a modified version of counterfort wall. You construct these counterforts. Similarly, buttress walls, both the purpose are same. Whenever you construct a long cantilever wall, definitely you will provide either the counterforts or you provide these buttresses. So these are the various types of rigid retaining walls. Now let us discuss the term shear failure in soils. So already in the previous semester we have learned what is the shear failure of a soil. That means whenever a soil is failing, and if the mobilized angle of friction or mobilized shear strength or cohesion, whatever, if the mobilized strength is higher than the actual shear strength of the soil, then that soil will fail. So this we have learned in slope stability in the final module of last subject, that is Geotechnical Engineering 1. If you recollect, you know that the slope generally fails when the mobilized shear strength is greater than the shear strength of the soil. So similarly here also, when we construct retaining wall, we have to consider this aspect of the soil failure. That means if the soil is failing, then definitely it will lead to the collapse of the retaining wall. So now let us see how this failure is occurring. So this already in slope stability we have discussed. So what actually happens is, this is the sliding surface or the failure surface, and the soil is moving down in this sloping direction. And what happens is that if the inherent shear strength of the soil is less than this mobilized shear resistance, then the soil will fail and this entire soil mass will topple down and leading to the collapse of the retaining wall. So this aspect we have to be very careful when we construct a retaining wall. Now moving on to the earth pressure. What are the different types of earth pressures? So there are three types of earth pressure. Earth pressure at rest condition, earth pressure for active case, and last is for passive case. So there are three earth pressure, and on what all factors the earth pressure is depending. It will definitely depend on the type or amount of the movement of wall. It will definitely depend on the strength parameter, that is shear strength of the soil, the unit weight of the soil. That means if you keep on going down, you can see that there will be change in the properties of soil, and this is slightly higher level. If you go to the more in deeper level, you will understand that soil properties will change with depth. So that is another thing, and also unit weight of soil. And then comes the drainage condition. Definitely there is, if you go with after some depth, definitely there is groundwater conditions. So based on that also, what kind of drainage condition is provided for a particular backfill, that is also affecting the earth pressure. So here we can see in the figure that the first case is there is no wall movement. You can say that the wall is at rest. So that is the at rest condition. In very simple ways, simple words, I can just from the figure you can figure out what is at rest pressure, that is wall is not moving. And active case, you can see here the wall is moving, slight movement is there, you can see the dotted line. The wall has slightly moved away from the soil, that is called the active case. And the third one is the passive case, where the wall is moving towards the soil. So practical examples definitely we will discuss when we are doing the numerical problems also. You can get a better understanding that what actually is the at rest condition, the active pressure and the passive pressure. So here in this figure you can clearly see that in the active case the wall is moving outward from the soil fill, and in the passive case the wall is moving towards the soil, and in the at rest condition the wall is standstill. There is no movement in the wall. Just understand this much, because this concept must be clear before solving any kind of problems associated with earth pressure and retaining wall. Now let us go into detail of what is earth pressure at rest and active case and passive case. So in at rest condition the wall is not moving. So there is no change in movement of the wall. That indicates that there is no displacement in the soil mass, or the soil is not deforming. So the earth pressure at that particular condition where the soil is not deforming, or the wall or the retaining wall is standstill, that condition is called the at rest pressure condition. Now what is active case? In active case what happens is that the wall, here you can see the wall is moving away from the soil. So that is an active case. So here you can see the earth pressure is acting in this direction, that is towards the wall the pressure is acting, and when the wall is moving means what happens, the earth pressure will reduce, and it will keep on reducing until a certain displacement, and then the wall will fail and this entire backfill material will slip down. So that is the active case condition. So if you see here in the figure, this vertical stress, it is the major principal stress, and this horizontal stress is the minor principal stress, because here the horizontal stress is reducing. That is why it is called it is a minor principal stress, and the vertical stress acting from top for this particular soil mass selected here, it is the a major principal stress. Just for understanding, need not go in too much into the detail of this, just understand what is the concept. Similarly, in the passive earth pressure condition, what happens is that the wall will move towards the soil, which will lead to an increase in the pressure. The earth pressure will keep on increasing, and what happens is that it will reach a maximum value, and finally the soil will fail. So here the failure actually occurs is that in such a way that the wall is trying to compress the soil mass, and the entire soil mass is compressed by this wall movement, and finally that entire soil mass will fail because of this excess earth pressure. So there are two cases. One is that the earth pressure keeps on reducing and that will lead to a failure, and another case is that earth pressure keeps on increasing and it will lead to a failure. So this can be very well represented by a graph here. You can see here a graph, the relationship between the lateral earth pressure and the movement of wall. So here you can see in the figure that the x-axis shows the direction of wall movement and the y-axis shows the pressure or the force on the wall. So you can see here at rest condition you have certain pressure called P0, and when the case is active, that is when the wall is moving away from the backfill, then the pressure is decreasing, and this is the active pressure. Let's say it's PA is the active pressure, and when the wall is moving away from the backfill, then the pressure is increasing, that is P0, PP, which is the passive earth pressure. So this figure, if you see, you can get a clear understanding that how the pressure is varying with the movement of the wall. So let us see here how you get that pressure. How will you find the earth pressure at rest condition. So no need to just go into the derivation part. I will just explain this, that here as the entire wall is not moving, you can see that the strain in the x direction, that is the wall is not moving in the lateral direction. So the strain in the x direction, you can get it as epsilon x is equal to 1 by E into sigma x minus mu into sigma z plus sigma y. Already you know this strain stresses, you have already studied in the mechanics of solids. And here as the soil is as this wall is at rest, or the pressure is at rest condition, that means there is no change in the sigma x and sigma y. Both sigma x and sigma y will be equal for at rest condition, and as a result of this there won't be any strain. So this epsilon x will be 0. The stress in the x direction as well as in the y direction are same, and as a result there is no strain developed in the soil. So epsilon x is 0. So this equation, you equate it to 0, you finally get sigma x in terms of sigma z, because sigma x is equal to sigma y. So you can take sigma x, that is the lateral stress, sigma x, you get it in terms of sigma z. Lateral stress is obtained in terms of the vertical stress. So it is sigma x equal to mu by 1 minus mu into sigma y, or you consider this, you take this mu by 1 minus mu as the coefficient of earth pressure, which is K naught. So K naught is the coefficient of earth pressure at rest condition. So you get the pressure at rest condition as P naught is equal to K naught into sigma z. So this expression is very important to find the pressure at rest condition. That is P naught is equal to K naught into sigma z, where K naught is mu by 1 minus mu, where mu is the Poisson's ratio. You already know that. So here the most important thing is, in this condition, the at rest condition, the stress in the x direction and the y direction are same. Here the z direction is in the downward direction, that must be very careful. And x direction, let us take this as the x direction, and the axis in this direction, that is perpendicular to x direction, is the y, the stress in the y direction. So both these stresses are same. So that is the at rest condition, and based on that we have got this equation P naught equal to K naught into sigma z. Just remember this equation to find the pressure at rest condition, and K naught is mu by 1 minus mu. Now here this is a table showing the coefficient of earth pressure at rest condition for various types of soils. So here it is actually tabulated here. In this table you can see there is the plasticity index as well as the K naught value. So for loose sand, dense sand, you don't have the plasticity index because they don't have the plastic characteristics. So for that the K naught value is given here, the pressure coefficient. So directly you can get the K naught value if you have the type of soil, and also it is given for compacted clay as well as organic silt. So here it has a IP value, and corresponding to that you have the coefficient of earth pressure. So earth pressure coefficient can be either found from the Poisson's ratio, or based on that particular soil. A lot of charts are available like this where you can directly obtain the earth pressure coefficient.